recording? Mm-hmm. Is there a red dot there?
Yeah.
All right, good. So, the first battery will look like this.
Good job, right? Yeah.
Like this?
That's what I thought.
I got it.
Okay.
Your thing's slow.
Are we yes, we are. A battery, let's say we have two different types of metal, copper and zinc. When you place copper into an acid bath and there's a chemical reaction occurring, the copper will lose electrons. So the copper gets a positive charge.
Are we going to do this? Can we do this?
You know, you can. I used to have a setup where we do this with 11 cents. A dime and a penny. Even though a penny isn't really copper, it works.
It's copper coated.
Yeah. If you use 11 cents and just a little piece of felt and salt water, you can do the same exact thing. So what happens is zinc in an acid bath is going to gain electrons. So you get this constantly positive and constantly negative charge. Okay, so you don't have to keep rubbing your feet and touching something. Alright? So what happens is, and remember we said, you know, if you touch something, if you have too many electrons, if you're negatively charged and you touch something, it's going to ground, it's going to want to always even out. Well, this will constantly want to keep evening out. Okay, all these excess electrons over here will want to keep going to where there's not enough electrons. And you get this steady flow of electrons. Now, here's where you're going to have to change the way you think about it though. Even though it really is that the electrons go from where there's too many to where there's too few, over the past hundreds of years of convention, every scientist, electrician, or electrical engineer will always say that current goes from positive to negative. Okay? And it's actually going against what the electrons are doing, but just don't think down to an electron. Current will always go from positive to negative. Always in electricity. Okay? Now you could do the same thing also with an apple. All right, and you notice there are certain like clocks. There's even some people that set up like a computer that would be based on this thing where you have two little spikes of metal, one copper, one zinc, and you place it in a potato or an orange, and it will run a clock or run a simple computer off of those two things. Okay, so if you're looking to be MacGyver, stranded on an island somewhere, find two metal spikes of different copper and zinc, and you can place it in I don't know, a pineapple and radio for help. Sound good?
Any fruit?
Well, no, it's really the acid. It's really the acid that has to go with it. Now, a couple of things I say here. We call it potential difference because there's a difference in charge. But we just call that voltage. So, Volta said, hey, my name's Volta. There's already something, no. Okay? Volta creates this idea of difference in charge, so we call it voltage. Alright? Voltage in a battery here, you're going to have direct current. Right? DC. Anytime you run off a battery, you have DC. Your car, the cigarette lighter, runs DC power. Okay? What do we run off of in any household or building?
DC.
What are we running off of here?
DC.
Nope.
Alternating current.
AC, alternating current. Okay?
AC.
In a car, you have 12 volts of direct current. Just a positive 12 volts. It doesn't change. I will be current. Okay? The current times the voltage is your power. Does anyone have parents or relatives that are electricians in here? Okay.
My uncle's an electrical engineer.
Okay. Even better.
No,
and an electrician has to use this formula every day. An electrician will always know, unless they're plugging into a dryer and they're going to run 240 volts, All right. Electrician will look at the power that it needs to run whatever it is. If it's 100-watt light bulbs, watts is power. Okay? So they would see that. So whether it's a ton of light bulbs or a hot tub, they would know how much power they need. Okay? And with that in mind, and knowing if it's 100, for most stuff 120 volts, they can figure out how much current's going to run through a wire. And you have different circuit breakers for it. Okay? If it's going to be a lower current, then you have you can use a smaller wire and you're going to have a different circuit breaker. If you're going to have a higher current, they're going to have to make sure they have a thicker wire. But electricians use this all the time. So even if they say, all right, let me see, I need 10 of these lights and they're going to all be on this circuit, then they'll look at the power, the watts it's given off, multiply them all together, divide by 120, and they know how much current they're going to have to use. Okay, that's what they have to do every day. All right, more units for your very important list. Power you should already have because that's watts. That was from work and energy also. Current is amperes, but we're going to just say amps. So you can just say amps there. Voltage is volts. All right. I say the reason I point this out is because current and voltage, not all cell phone chargers are built the same. Now, most cell phones are going to be smartphones where you have either a USB, mini USB, micro USB, or iPhone. And so they're a lot more common. But 5 years ago, all cell phones had their own different plugs. Okay? And yeah, it was terrible. But here's the even worse part. Even if it had the same plug, if the plug size could have been the same, but the voltage was different. So you're looking around for a cell phone charger, and you say, oh, this will fit. You plug it in, and you could kill your cell phone because it says on every power converter, okay, on every power converter, it's going to say the output in voltage and the current, the amps. Voltage and amps, okay? It's going to tell you what these two are. And just because this plug fits, okay, into whatever you need to use it for, it could still blow the circuit. Okay, so you want to look. Like this one says, now every single plug is going to say input 120 volts. Because always, we know, anytime you plug something in the United States, you're going to get 120 volts AC. But it says output is going to be 6 volts DC. Okay, and it also gives you 300 milliamps. So it gives you the current. It gives you the current, milliamps, and it gives you the voltage. Okay? So then when you plug something, if you're not sure, just look at what the output is on this, and look at what the input is for whatever you're plugging into. Okay, and just make sure those match up. Sound good?
What do you find that on the cell phone?
Usually it's near the battery case. Or like if you take the battery off, it might say in there. With the iPhone, you can't open it up. But the iPhone has its own plug anyways, you know? And fortunately now there's only really 3. Micro USB, mini USB, or an iPhone.
Does anyone have a micro?
Blackberry.
I have a micro. Okay. Huh? It's plugged into my external hard drive right now. We'll talk later. Okay. Don't worry about this right now. Here is a circuit. If anyone has Mr. Ickes, if anyone's dealt with circuits before, okay. I don't know what he does. I remember other circuit classes before would tell me, you know, the kids would come and say, that's not a battery, that's a cell. I don't care. This is what we're going to draw a battery to be. Okay? Long line, short line, that's it. Long line will always be the positive side, short line will always be the negative. Positive, negative.
You want us to draw it?
I do. I'll let you copy right now. Go ahead and copy that down. And we will pause. Alright. Which way does current always flow? From positive to negative. So you know that current will always go in this direction here because we're going from positive to negative. So here's your current. Okay? Ohm's law, V equals IR. Whatever you need, you'll just cover up to solve for. Okay, so then figure out if it's going to be division or multiplication or anything else. Here's another thing that you should add to your very important list: resistance. A resistor, the units for resistance are ohms, which we use omega. 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 Okay? To figure, let's say I want to figure out the current running through here. Let's say I have 120 volts. Let's say it's a battery, or plug it in the wall. Let's say that I say this is a 10 ohm resistor. How much current is running through this circuit? 12. 120 divided by 10 will give me my current. So I just figured out using Ohm's law that the current equals 12 amps. Okay? We will have down the road more complex circuits. We could have series, we could have parallel. But basically they all can be boiled down to one resistor and one power supply. Most times when electricians have to figure out what's going to be going on, they just want to say, all right, what's the equivalent resistance? What's the big resistor that's going to be pulling on here? And they're talking about simplifying to one. And I'll talk about that in a bit. All right, now, it's not really voltage that kills you, it's the current running through your body. So you could actually touch something that's 120,000 volts. But if no current runs through, you'll be safe. All right? But if, let's say here, I touch this. If I stick a paper clip in here right now, I'm going to get a shock and it's going to hurt. Right? I'm not going to feel good for a little bit. But I'm not going to die. Now, if I'm standing in a bathtub filled with water and I do that, I'm probably going to die. Alright? Now, actually, a quick little side note, just so you know what it is. This button is a GFI, a ground fault indicator. And in classrooms, they'll always have GFIs. In your bathroom, in your kitchen, and actually all the outlets outside will be running off a GFI. And you'll see in the kitchen, you have the two buttons in between the outlets. You have test and you have reset. That's so that, you know, somebody doesn't try to throw their hairdryer in a bathtub or something like that. Now again, don't try it at home, and I'm not going to rely on that GFI. I'm going to make sure the hairdryer isn't anywhere near the bathtub. But those are set up so that if it all of a sudden got a spike in current, it would automatically shut off. Okay, it wouldn't wait for the circuit breaker downstairs to shut off. Anyways, so the reason that if I touch this wire when I'm standing in water, okay, standing in water will decrease my resistance. Right now I have rubber sole shoes, okay, I'm not a good resistor in general, I'm not good at conductor in general, so current doesn't want to flow through me if I just touch it. It will a little bit, and it's going to hurt, but it's not going to flow that easily. If I stand in a body of water while I do this, current can flow much easier through me, and just 0.07 amps could kill me. Okay? And what happens when you get shocked is if you touch something, when the current runs through, your muscles all tense up and you can't release. You can't let go of the object. Alright, now here's a story. It was during the '96 Olympics, and I was a security guard for the Centennial Olympic Park. And on the far end of the park, there was an electrician working on a transformer just before the Olympics, and he grabbed a wire that was hot, and he got electrocuted. As he was getting electrocuted, his friend saw him there, another electrician saw him, and decides to try to grab him to pull him off. Well, the problem with that is if you grab somebody, then the current is now running through you. So he was stuck as well. And so, I mean, you laugh, but they died like that. I mean, it's not that funny. So as soon as he grabbed them, I mean, we're talking about like 10,000 volts. So he was electrocuted as well. All right, so not that this would ever happen, but if you ever saw somebody getting shocked,
Tackle.
almost. If you saw somebody getting shocked, you do not want to grab the person and pull them off, or you get shocked also and you get stuck. Don't kick them. Okay, you'll get stuck also. You want to run, you want to dive, and you want to lay them the hell out. Okay? You want to run at them, you want to leave your feet, and you want to be horizontal as you knock them over. Okay? You don't want to, the reason you want to run is you want to have momentum. You don't want to have to stop and complete that circuit. You want to run into them, but you want to, once you knock into them, you want to be still far away from the circuit. Yes?
I've electrocuted myself with a fan before.
With
on a metal ladder too.
Well, just so you know, you didn't electrocute yourself, you shocked yourself. The difference between electrocution and shock is you're dead if you electrocute yourself.
When I shocked myself,
It was bad.
they gave me dead arm.
Yeah, yeah. I worked as an electrician one summer, or as a helper for an electrician, and I was good up until like the last day when I had to show somebody something and we couldn't turn off the breaker. Totally forgot and grabbed it.
I was about to turn off the breaker and I just touched the little metal plate to a live wire and I was like, oh, shoot.
Yeah, yeah. Doesn't feel good.
No.
Okay, so anyways, yeah. Hopefully you never see that, but if you do see someone getting shocked, don't try to grab that person. Lay him out.
I'm a Bruce Lee kick him in the face.
As long as you don't have the
Do you
Yeah.
have to copy?
Huh?
Do you have to copy?
No, don't copy this.
Mr. Spudek.
One, yeah, let's pause, and yes. Ryan gets a gold star. Okay. Here is a series circuit. Are you ready? You ready to be shocked and awed?
We should turn off the lights.
We should turn off the lights.
Here we go. Ready?
Yeah, Jacob.
Matt, get it.
This is 3 light bulbs in series. So from 4th grade, you remember one. When you have, let's say that I have a 4 ohm resistor in parallel with a 4 ohm resistor. Here's what happens. When you have 2 resistors in parallel, and for most of the time we're going to do it, they'll be the same number to make our lives easier. The resistance goes down when you add more and more things in parallel. Okay, so if I just had one 4 ohm resistor, let's pretend this other one isn't here. My total resistance is 4. But if I have 2 4 ohm resistors in parallel, they're going to get cut down. Because the equation is going to be this right here. 1 over R total equals 1 over R1 plus 1 over R2. But really it's just going to be this. My total resistance is going to be 4, because I have a 4 ohm resistor, divided by 2, because there's 2 of them. So my total resistance will be only 2 ohms. And so the shortcut I'm telling you is, anytime I give you parallel resistors, if you have them the same number, you can just figure out how many there are with the same number and divide them by the number there are.
It's not the same number.
If they're not the same number, then you're going to have to do some algebra. I'm hoping that there will be all the same number. Okay? But this part here, so there's a little shortcut, and you'll have some problems you have to do that. But this part here is actually pretty important. Okay, because what that means is that anytime you plug stuff in, again, our houses are all wired in parallel. Thank goodness. Okay, another part about it that's important is that if this is 120 volts here, anything in parallel will always be the same voltage. So anything in parallel will have the same voltage that it's in parallel with. So if this is 120, you know that anything you plug in, anything you add to it will always get your 120 volts. And that's good, okay? Because since our house is wired in parallel, it doesn't matter how many things I plug in, I know I'm going to get 120 volts. That's good, right? But here's the one thing you need to know about. Let's say you are, let's say HK is getting ready to go out, so he's doing his hair in the bathroom, plugs in his hair dryer, okay? Plugs in his curling iron.
I think Vince needs to throw in a straightener.
Oh, that's huge.
Vince, yeah, okay.
We can go with HK.
We'll go with HK.
But you can apply this to your life too, Vince.
HK then has, so he has a curling iron for one side, straightening iron for the other. He's going for like a flock of seagulls kind of thing. Alright, now, he wants to plug in his stereo because he needs to dance while he does his hair. Alright. Then he wants, he plugs in his microwave too because he wants a Hot Pocket while he's getting ready. Alright. He has a mini fridge which carries all his bottled water, his special bottled water, so he has another thing plugged in.
Sparkling water?
Yes, exactly, sparkling water. What happens when you plug too many things into one circuit in your house? It doesn't blow up or you'd all be...
Power slow.
The circuit breaks, okay? You have a circuit breaker in your house and yeah, it pops, okay? It triggers the circuit breaker and it pops. The reason it does that is every time you add a new resistor in parallel, the total resistance goes down. And if the total resistance goes down, the current goes up. So you get more and more current running through that wire. If you have too much current running through a wire, it's gonna cause a fire. The wire is gonna get hot and it can actually cause a fire. Okay? So your circuit breaker is there to make sure that if you plug too many things in parallel, if the current starts running too much, the circuit breaker will pop to tell you, hey, you don't need to do your curling iron and your microwave. Okay? But that's why your circuit breaker pops. Because every time you plug something more in, the total resistance actually goes down, not up.
And that's why when sometimes you plug something in, you see the lights dim in your house?
Yeah.
Like when you start your hair dryer or something, then...
But it's only for a second. It draws it and then it, yeah.
Okay.
Or sometimes when you're air
But you can see the... Yeah.
Yeah. Okay. We'll pause.